So I guess I'll be talking about the work I've been doing over the summer and a lot of last semester, trying to develop heuristics for incorporating sims into assignments. So just an overview here. First I'll talk about some of the goals of this and the work I've been doing. And then I'll go into more specifics. The first is a case study of the build a molecule sim used in a middle school classroom, and then a quantum tunneling sim used in modern physics. And then I'll go into this framework that I'm using to kind of analyze this and talk about future work. So overall, the goal for this project was just to figure out how to incorporate sims into these assignments and what some of the things you need to account for are. And so far, we feel like there are two parts. So there's this set of heuristics, and then also understanding how to apply these heuristics in different contexts, and which heuristics are most important in different situations.
Excuse me, Danny, is there something in the way of the projector?
No, that's the background. That's the background.
Oh, I
the
see.
screen.
Okay, sorry.
So last semester, I collected data in several different classes. So two of those were in Class Mech 1, using the projectile motion and resonance sims. Two of them were in Physics of Everyday Life 2, using Snell's Law and lasers. And then the two I'll focus on here, obviously, are the tunneling, and so that's in the engineering modern physics course, and build a molecule in the middle school classroom. So some of the data I've been collecting are observations of the students and field notes, survey responses from the students, audio of the students using the assignments, and Camtasia files, which are just like screen capture plus audio. And then also instructor surveys and my notes about what I tried to do developing these, and also research from prior literature that had data that's kind of useful to take note of. Then obviously the summer I've been analyzing that data, trying to interpret the findings and developing a framework. And then revising heuristics, research on prior literature, etc. So this first case study is the build a molecule sim. And I don't know if you guys have seen this, so I'm sure most people probably have, but
Very not. It's very cool. It's new.
It's relatively new, so.
yeah. So
And it's chemistry. Well, quantum physics, sorry.
So here's the general layout. So you can drag these atoms around, and for instance, I can make water here, and then this box blinks up, and usually it says you can drag it over there, and kind of the bell rings. And then there are these different tabs. So the structure of the assignment followed these different tabs. So here you're just making one molecule. In this tab you're making a certain number of molecules, like 2 CO2, and then this tab is totally free form, and the students can just build whatever they want.
How many different kits are there? In the bottom?
3 and 5.
3.
Yeah. 5. Actually, they keep going.
Oh.
When you get done with one kit, there's another one. I don't know how far it goes.
Okay.
So some of the learning goals that are actually listed on this assignment are describe the difference between chemical formulas and chemical names, distinguish between the subscripts and coefficients, and use pictorial representations of these molecules to generate a chemical formula. And so a little bit about how the students were situated in this environment was they're basically in groups of 4 sitting at tables, but each student had their own computer and their own assignment. So, in general, it was pretty much an individual effort. They didn't talk a whole lot to each other. And also the teacher did a good job of trying to move everyone on from one tab to the other. So once she felt that everyone was almost done, she would, with one tab, she would collectively move the class to the next tab.
And this was a middle school?
Yeah. Um, and then, so I've already said this, but that's the data collected, and I tried to take notes on what the students were doing, some of the things that they said that stuck out. So some of the findings here were that the phrasing or structure of the sim, or of the questions in the assignment allowed for playing with the sim, and I'll go into each one of these in more detail here, but also the constraints of the sim seem to really guide the students' reasoning, and sort of one unexpected thing was that the students had to write down like chemical names and formulas, and I felt like this really helped them to internalize things that they saw in the sim. That, you know, if you hadn't forced them to write these things down, they might not have internalized it quite as well. And then also, this last one is asking about visual features can make apparent parts of the sim that might otherwise go unnoticed. And where this came up was that, like, one of the first questions on the assignment asked the students, you know, like, how do you know that you made a molecule? And the whole point was that they needed to understand that the chemical name would come up above whatever molecule they made. And so they, you know, like, that might have otherwise gone unnoticed because you can make like molecules that don't have like a formal chemical name. And so later on in the assignment, when they're asked to build the largest molecule possible, they needed to kind of understand that, you know, there's a difference between those two types. So basically where this play was really apparent in the Camtasia videos. So what you would see is the students would play with the sim for a long time, then they would stop and go on and answer questions. And so here's an example of one of the questions on the sim. And so they've just got this table, and like they're asked to write down molecule name and the drawing and what the formula is. So it's really open-ended. There's no instructions on how to do this. It's pretty much just they get to choose which molecules they want to write down. And surprisingly, they didn't seem to like play with the sim a little bit, figure out one molecule, and then write it down, and then move on and play again. They would play with the sim for, you know, several minutes at a time, and then return to this. And one reason for that might be about with the game-like situation present in the sim itself. So, I mean, if you saw, you know, you have to drag the molecules over, and there's kind of like this implicit game-like scenario already present.
This is literally the second challenge on the worksheet. Number 2.
Yeah, this is dealing with the first tab, but yeah, this is like the second challenge.
But impressive because this is the first time they're seeing the sim, or the second question in which they're interacting with the sim, and it's to come out and do something that could look to be fairly sophisticated to coordinate between molecular name, representational drawings, and chemical formula.
So some of the constraints while playing with the sim, I actually want to show a video that's really interesting here. And so the audio is really not all that important. And let's see. So you can just kind of watch this. But basically the student's trying to finish the 2NH3 box over here on the right. And you can see he's already associated 2NH3, meaning 2 nitrogens bonded together, which is incorrect. And then that constraint on the sim won't allow him to place that over in the right box.
Try it again. Big the scissors.
And so finally he gets it. But I guess
Looks like that's one end of the street.
yeah, he actually never moves on and creates the second one, and I'm not exactly sure why.
Because it didn't relax, that he's done maybe.
Yeah,
But
he,
he'd already done the other one, so.
Would
right.
it, does the sim, just to speak exactly to this issue of constraints, will the sim let him move, I guess the sim will let you move on whenever.
It'll let you.
But it doesn't, the question is do the sim let you know that you've completed a task versus not complete the task and filling in the box? So it's halfway done with that
Well,
box.
it said there was a little tiny thing that said you have one
Yeah.
and each three.
Oh.
You get a nice.
It was really tiny though. Right there underneath,
Yeah, right there.
goal, and it says
So-
you have one. It's really tiny.
This also.
Oh, you have one. Oh, I thought W-O-N.
Yeah.
No.
No.
Okay.
This also might be not the latest version because something I think we added is that in boxes that should have two.
Right.
Instead of being in the center, it's off to the
To the
side,
left.
so you see that there's space for another one.
And am I seeing, it's a little hard to see on the screen, is there like some sort of frame on the ones where he's achieved the goal?
Yes.
Yeah, it's a yellow. So there's like a yellow
So
box.
there's a yellow
No,
frame.
It's gold.
It's gold, right?
Yes.
Okay.
You can't move on to the next level
Okay.
until you fill them all. But you can move between tabs.
Right. Okay.
And also, I don't know. They might have been close to moving on at this point too, so that might have influenced the reason why he didn't continue. But some of the main points here is that, so you want to promote play mostly because it allows for error. Maybe not mostly because it allows for that, but so it allows for error, and then the constraints can show the student that an error was made. And then the student was obviously forced to reevaluate. And then I guess the question you can ask is this evidence that the student learned? And so some of the main points here are that constraints guide the student's reasoning, and that play is often necessary for effective use of those constraints. So moving on to the other topic, which is the effect of writing. The students were asked to write down these formulas, and this provided some kind of mechanism for internalizing what those different formulas and pictures meant. And reasons for that might be that they have time to reflect on what's shown on the sim itself, and this actually forces the students to look a lot more carefully at what's shown. So, I guess playing with the sim, and then you see like the 3D picture of a molecule, seeing it up there is one thing, but then actually having to sit down and draw what it looks like is totally different. I mean, I don't know that I can just like look at something and instantly know how to draw it. I have to like look at it a few times and really analyze it a lot more.
Dan, is that your hypothesis, or do you have evidence to support that claim?
This is more a hypothesis. Yeah.
Well, but it's drawn from your observations of what students are doing. In
Yeah.
fact, so writing was not initially sort of key heuristic in the use of these sims.
Right, that's exactly what I'm wondering, is what like you've made the claim that it is the writing which is providing a mechanism for internalizing something. And so there's a couple of elements there, like how did you know that they had internalized something? And
So yeah, I should have probably mentioned that, but the students were asked to do like a pre-test and a post-test. And
good.
so there were, like basically the pre-test, as you might expect, was a lot of errors, not much right. And then in the post-test, a lot of the pictures that you would see the students drawing were like three-dimensional representations of the molecules and things. So I just, based on that observation, I mean, I don't have evidence that students who didn't write anything down would be able to do that, but it was kind of an assumption that this probably helped in some way.
Yeah, and it also comes from, I mean, you're coming up with another great list of stuff that you should be reading here. But, thought and language from Vygotsky argues this very strongly, that language itself is a key mediator in the cognitive process. Writing is a key act in both mastery and reflection on language itself and the use of language in the representation or representation of ideas. So I mean, it's consistent with what's in the literature that you haven't yet read, but I'm sure you will now.
So could I bring up a really quick question? So you mentioned about pre and post test assessment, right? See if they learn from this whole process. But I'm curious as to whether you did any investigation on the playing phase, so that you take a look at how much time that was spent actually tinkering back and forth, and did they spend a lot of time just simply tinkering, or did they actually by trial and error rather than learning something in that process of just playing, or did the learning come out in the end after they went through the writing process? So what I'm saying is more spending time looking at whether they learned when they were tinkering with the application itself, the Sims thing. Because I see a lot of students, they can get in that position, and I'm just wondering where they simply just try every single way to do it, and eventually one works, and then but so being able to try to assess that versus,
We call that engineering.
yeah, so okay, yeah, all right. So were they tinkering, or were they actually kind of really starting to learn something there by tinkering? Then maybe looking at the time that they spent on each, trying to formulate each little molecule.
Just the number
Yeah.
of attempts.
The number of times.
Number of attempts to make.
Yeah. So was that
Right. Well, that's what I was going to say, is that I don't think you would learn as much by just tinkering one time, but over that accumulated number of times of building multiple molecules, I think you're going to start to internalize some of those some of the rules, like 2O2 means you have to build 2 oxygens, and 2H2 means you have to build 2 hydrogen molecules. So I
So
think
you can see whether or not that process changes over time.
Right.
That is do they get better at doing 2O2 after? I mean, and by better, which is, do they do it faster? I don't know if that's better, to be honest. And it's an interesting question about
That's
where
what
does
I'm
learning
asking.
happen. So you didn't look at it so much at that scale.
Yeah, I didn't look at it too much. There is evidence of that in the video, though. Like right before this student was making 2NH3, he made maybe 2H2 first, and then immediately after he made that, he went and made 2O2 really quickly, and then
Okay.
2N2 really quickly. So yeah, I could look at it in more detail, but I have a feeling that there's different. Playing with the sim satisfies certain learning goals, and writing it down satisfies others. So I think it's
Right.
a different type of.
Right. I mean, I think there's a whole thing within that Sims, looking at how they learn just in that area that could be expanded on as well.
Yeah.
I would actually rephrase the question a little bit because of what we've seen students get out of that play time, which is, say, what are students getting out of that free play time? And when you start asking, what did they learn, or are they learning, that presupposes a certain thing that you're going to observe that's evidence of learning, which is they did better on the pre-post test or something like that. But there are other things they can be gained. So the question I like is, what are students getting out of that time? It might lead to more formal learning later, or it might be something completely different.
Right. I even changed that question myself, to continue, which is, we act as though we collectively know what the word play is, but in fact I think it may be very different for those of us. And so this is another reading that you've actually already created for yourself, which is Vygotsky on play, which is to say play is a mechanism by which we test the bounds of formal reality and understand where the bounds of realistic systems are by creating imaginary worlds that we pop into around. And whether those are imaginary worlds within the PhET imaginary world or imaginary worlds in our real world playing with horses or whatever it happens to be. So it's an interesting thing about what is it that play is and what is it that it does for us. And there's argument, at least in some psychology, that it plays an incredibly important purpose as a mechanism or as a process of learning.
One of the things we see is that students take more ownership over the whole learning, the whole activity and process of using the simulation when they're given this free time to sort of explore. At least we see that with middle school students. So I don't know whether...
I'm going to try that with grad students. They're going to be in charge of the entire course.
Well, I mean, one of the weird things is that by the time people get to college or graduate school, they may be more indoctrinated into what am I supposed to be doing, and not actually reaping as much benefit from just saying do whatever you want for 5 minutes. So I'm curious whether you see students just digging in and playing, and taking over and thinking this space, this thing that I'm playing with is mine, and I'm not going to use it to learn from, or whether they kind of go back to.
I'll get to evidence of that not happening. So some heuristics I think can be drawn from this assignment are first that you want to set up game-like situations. So this has a game-like situation kind of implicit in the sim itself. And then this idea of asking students to recreate or represent visual features on the sim. And ask about visual features, just what I was talking about real briefly early on with asking them, like, how do you know you made a molecule? So the second case study here is the quantum tunneling tutorial in modern physics. And so last semester I wrote 2 different versions of this tutorial. One used the FETSIM and one didn't. And then I audio recorded 2 groups of students. And then this summer analyzing and trying to draw heuristics. So some of the findings here, one was that the students using the non-FET tutorial were much more engaged in conversation. So there were 4 students that asked 90 questions. This is amongst themselves. And then the FET group asked 27 questions. And that was 3 students total. And then also one thing that was really noticeable was that the types of questions were radically different in both cases. And I'll get to more details about that in a minute. And then also the students' use of math is totally different in the 2 cases. So here's an example of what was asked. This first part of the assignment was the same for both tutorials. And basically it was just an analogy to classical physics. So you have a ball rolling over a hill, and some of the questions that we asked were, what's the kinetic energy of the ball in region 1 versus region 2 versus region 3, and then we asked about probability and the time it would spend. And the whole point we wanted them to take away from this was that, because the ball rolls slower on the top of the hill, there's a greater probability of finding it there than in either of those other regions separately. And so the whole idea was to relate this to the quantum case. So actually, before I discuss this, so the FET tutorial went straight to the sim, and I started asking them questions about things that are shown on the sim, and the non-FET tutorial went straight to math. And so we started asking, like, well, if E is greater than V, what's the solution? And do you have sines or cosines and things like that? And so anyways, a slightly different format for both. But I thought that the conceptual ideas would be the same in each case. And so here's the sim. You've basically got your total energy here, and you can adjust this up and down. And one idea that we're asking about is, how does the wavelength compare in the regions? And so, you expect a greater wavelength in the middle region because there's less kinetic energy. And then we also ask about, so what does that mean for the probability density? And so we're trying to get them to associate less kinetic energy with, on average, greater probability density. And that's not exactly a true statement. So, for instance, down here you have the probability density, and it's almost the same as it is in the left line.
What did you just do?
I just am adjusting the barrier width.
So is the product reflection off the rear wall?
Yeah, and
It's artificial also because
plane wave, and that's why you have modulation and probably have electric barrier.
Yeah. Right.
I didn't hear that. What?
Well, this is a plane wave, which is
Yeah.
a constructed situation.
So you have the modulated probability density from the reflected plus incoming.
Go ahead and just separate the waves just so people can see on the right side.
Oh, okay.
So I mean, this is another way of looking at it. You've got transmitted and reflected waves. And this is about transmission and reflection, sort of. But this is a fake situation because you can't ever have a plane wave. But we teach it all the time.
Yeah, and I guess the main goal here was just for them to associate the larger wavelength with less kinetic energy and on average, greater probability in that region. And then, so...
But also, it also demonstrates sort of the dual phenomenon of tunneling, which is reflection when you have enough energy go through the barrier.
Right. Yeah. Yeah, so I mean, there are cases where you can get a lot of reflection, and then your probability density is a lot different in like the left region compared to the right region. So it's not, I mean, it's not a perfect analogy, but I mean, it was, you know, it's difficult to know exactly how much you want to teach in this class since you don't get into reflection and transmission coefficients all that much. So basically we start out with this case of E greater than V in the tutorial and go through a series of questions that try to establish this point. And then we ask them, you know, so what happens when you have this case of E or of E less than V? And so obviously the classical case, classically there's no analog, like, you know, these other two regions 2 and 3 just don't exist in the classical case. So basically what we wanted to ask was, you know, if you're using this idea of the kinetic energy in regions 1 and 3 being the same, leading to roughly equal probability of finding it in those regions, then how do you explain this, where the probability density is totally different in the right region? And so, I recorded some. I took notes of one of the conversations in the non-FET group, and here's what they discussed. So student 4 says the reasoning we used before, at least I did, was that because the velocities were slower in the one spot, meaning the middle region, then it had a higher probability of being found there. So if they're equal, they should have an equal probability, and their amplitude should be equal, right? Right, well that makes sense in terms of equations, but like he said, I'm not sure you can think of it in the classical way, like 1/2 mv squared. I know that lower amplitude in region 3 is what it should be, but I want to be able to prove it to myself. So this is kind of what we wanted them to go through and to struggle with. On the other hand, in the FET group, there was really no analogous reason. So there was no evidence of them really questioning why is the amplitude different in these regions. And instead, an example of what they asked was, so student 1 says, that one's still a sine, right? And they're like pointing to the sim while this is happening. Like if you decrease it, is it still sine or is it always 0? And student 2 just says, well, technically this is still a sine wave. And so this example here is actually very representative of most of the questions asked throughout this FET tutorial. So it's almost always about things that are shown on the sim and not so much about the underlying physics. Okay, some additional concerns with the FET tutorial here. So basically, prior to handing this out, we had developed a list of heuristics that we thought would be important. One of those heuristics was set up the sim to look at illuminated cases. And so I implemented that.
Just as an aside, this is sort of plays on Mahajan's plays. We always talk about extreme cases in physics, And Mahajan has been arguing, no. There are more than simply extreme cases, not simply the endpoints of a system. There are illuminating cases. Like sometimes even Stephen is a really important case to be looking at in that. So that's where we get the term illuminating case and this idea.
Yeah. So here's how I implemented this, and I say, so now using the FET sim, decrease the size of the wire gap to 1 dash line wide and increase the height of the potential energy all the way to the top. And what type of function do you see? So, without even really thinking about it, I was all of a sudden telling the students exactly what to do. So what problems did this create? First, it led the students to waiting for the instructor, for the tutorial to tell them what to do. They weren't like, figuring out what to do on their own or trying to answer questions on their own. They didn't feel like they could play with the sim. In one case, actually, one of the students asked me to set the sim up for them because they didn't know how to, or they didn't feel like they were doing it right. Little interactive engagement and no sense of ownership. And also this, I think, limited the students' conversations. So, rather than really discussing like why they're seeing certain things on the sim, they're just going through and setting it up and writing down the answer. So
So we call that a success.
Well, it was illuminating.
So some of the points to take away here is that sims aren't necessarily bad.
I like that conclusion.
But this assignment just didn't work. And the use of the sim was obviously influenced by the assignment, and we need to better understand how to write these assignments. So some of the heuristics, John, basically, maybe before I say this first one, I should explain a little more about the non-FET tutorial and how what the role of math in that tutorial was. So the students, obviously, they're asked to solve the equations, and then for the case of like E greater than V or E less than V, and then after that, they're asked to actually plot a wave function. So they have to actually draw what the wave function looks like and what it does at the boundaries. And it actually worked quite well if you watch or look at the audio. And so one heuristic drawn from that is that maybe we can use these sims to coordinate other forms of representation. So maybe we should have started with the math and then used the sim to draw out some of the things that are different between what they thought mathematically would happen and what actually is shown. So that's one heuristic. Again, set up game-like situations. That seems to kind of just pop up everywhere and helps the students to play more with the sim. And then, possibly using the sim to mediate discussion. So in this case, obviously, it didn't do a great job of that, but it did do something, not exactly what we wanted it to. And then also utilize illuminating cases. And the main point about these last two is that how you present these in the assignment really makes it a dramatic difference in what the students do. So, trying to use an illuminating case by telling the students what to do is different than asking about a particular feature. Like, maybe an illuminating case is maximum reflection, and you ask about that, or what the conditions for maximum reflection are. So in a way, you could imagine using illuminating cases along with setting up game-like situations. So with those heuristics, one thing we felt was that the heuristics in themselves weren't enough to account for when to use them and how to apply those. So we came up with this framework, and basically you have features of the sim over here on the left, environment, situation, and then assignment here. And The main idea is that the features of the sim are going to influence both the environment, so like what the student is doing, and maybe what questions the student asks of the teacher about the sim itself, or so it's influencing the environment, and it's also influencing the assignment, or how you want to write the assignment. So, in the case of build a molecule, there's the sim has an implicit game-like structure in it, so you don't need to ask a lot of questions about to try to set up game-like situations, whereas maybe in the tunneling tutorial you do. And then over here on the right, you have the assignment affecting the environment, so that affects what the student's working on. And in addition, the environment is going to affect how the assignment is written. So, for instance, if it's a homework assignment, you're not going to want to write the assignment to be used to mediate discussion, or to like have the students start talking with each other. So here's just here's all the more complete list of the heuristics that we've found so far, and I won't go through these, but so basically there's more, and these are drawn from the other assignments I've looked at. And the whole idea is that these heuristics really come into play as a piece of this framework. So you want to employ these heuristics by like taking particular features of the sim and then seeing which heuristics apply to those features, and also seeing which features of the environment are going to be which heuristics are most important for different environments. So that's kind of the general idea. And then actually I'm going to skip this. This was just about a camp that we did last week or 2 weeks ago. And it skipped the wrong slide. But so the other slide was about future work. And so basically in the future I'm just going to keep trying to refine these heuristics, and also really start to determine which heuristics are most important in different environments, and in using for particular features of the sim.
So one question I had, so like when you're talking about the game-like features that might be different in different sims, like the make a molecule sim might have it kind of built into the structure, but the other one doesn't. Like, have you talked to the sim developers to figure out like from their point of view which ones have a built-in game-like structure, or like any of these other things kind of built in?
Not so much yet. I feel like you can kind of tell usually pretty.
If you have to answer that question by talking to the developers have failed. It should be self-evident whether there's a game-like feel or part of the sim or not.
Yeah, but you'd still have to go through a list of like 100 of those, and then check them out and see for yourself. If
it's an obvious like segregation into game-like and not game-like, then is that just one of the things you can sort by on the website, or should it be? If it influences instruction.
Game-like or not game-like depends as much on the sim as the people who are using it.
Yeah.
And what we've actually seen is that there are many sims that I would say are not game-like sims. The kids turn into games. In fact, I would say every single sim we put in front of the kid gets turned into a game except for magnet and compass. Because all it has is a bar magnet and a compass. They try really hard, but everything else gets turned into a game. Things that we didn't expect. So it's not completely self-evident which ones could be game-like if in the hands of the right.
As a specific example, like Mike's just working on a sim for normal modes I've been doing some interviews on, and you can see when you do this with physics majors, there's no game-like scenario in the sim. But when students see the 2D,
You talk about boinga boinga boinga.
I mean, they try to do different things.
Right.
Oh, let me see if I can do this. Let me see if I can do that. And they make an internal game if these are, junior physics majors. So,
I'll tell you what, when I saw that 2D, the first thing I tried to do was see what would happen if I turned on every single normal mode.
so I mean, there's a game-like component to the way someone's playing with it. They
Right.
kind of make up these personal goals as they're doing it. Like, oh, I wonder if I can do this. I wonder what this does. And that seems, I don't know if you call that game-like or not. There's not like a little timer and points for which normal modes you can recite. But,
Well, actually, yeah. Some of the, sorry.
yeah.
I was just going to say, if you need to put in a timer and scores, then well, we have some sims that actually work pretty well that have a score built into them. But for the most part, if you try to make it explicitly like a game with timers and scores, it's not the optimal game-like sort of thing. The game-like really needs to be an implicit challenge that people discover then try to solve. So if you force it, it actually
That would be a
doesn't
good
work as well.
verbiage for what you're saying in your study is implicit challenge versus game-like.
Well, right. I think actually game-like might be the wrong word. And the idea is promoting play, and this is actually where we can draw on a psychology of play as distinguished from gaming. And this is, in fact, maybe something that's sort of a deeper enterprise as to why the gaming movement is not as catchy as the national scene would like it to be, perhaps.
The game.
Oh, the movement that all we need to do is to have students play video games in order to learn physics.
That's because as soon as you put physics content into a game, it's not fun anymore.
Hey, that makes sense to a physicist.
Every game that I've seen that
Right.
puts explicit content into it is not as much fun.
Right. Well, it
there's
depends what you
something-
mean by fun. And anyway, but the point is I think there's this idea of play and exploration that is and can be and should be distinguished from gaming.
And lots of the most popular games out right now have no score and no timer, and
Right.
often no clear challenge.
Right.
No,
Like sim games.
No clear challenge.
Right.
No end point.
Yeah. But what do you think, Danny, about? I mean, so what would you do to switch the quantum tutorial around? Yeah. I mean, so there are thoughts to revise that and try and run it again, right?
Yeah.
And so, right. So, I mean, and you could argue that the tutorial itself was broken, or it did, what it was designed to do, which was drive people mad. And, that it didn't achieve the goals that you had, which is great, and I love that representation of it. Presenting that is really important. You could say, well, it's the tutorial, or you could say, you know what, by the time students get into college like this, they're so constrained to follow certain norms that they wouldn't play like the middle school kids. I doubt it, because you saw, well, anyway, I suspect we can get kids
Well,
playing.
they're not just college students, they're mostly engineers, right?
They, yes, are mostly. Anyway, so let's turn it over to Danny and Charlie here. Yeah.
Well, so I have written a new tutorial. It's for upper division quantum, not modern physics. So we can talk more about reflection and transmission. But basically, the way it's structured is that first we ask them to just write down the general solutions in each of those regions, and then try to draw a picture of the wave function. And then after that, we kind of assume that they're going to draw the wave function wrong. So we start asking questions about what should the wavelength be, or did you take account of the wavelength in regions being different and all of that. So we basically set it up for them to fail at drawing the wave function. And then we ask about it, and then we move on to the sim, which shows the correct picture, and try to get them to start comparing what they thought to what they see. And the questions in the sim part are a lot more open-ended. So we say what parameters can you adjust to maximize transmission? Or, how do you maximize reflection? Things like that. So we just basically stay away from telling them, okay, set up the sim this way and write down what the answer is.
Another. Oh, go ahead.
Are
Charlie.
you doing any more with the middle school stuff? Or do you have plans to?
I don't have plans to right now.
Okay. Because, FET has a whole grant right now towards middle school, developing sims for middle school and understanding how to write activities and developing a framework for that.
That's going to be a great master's thesis,
So
Danny.
you should coordinate with us. And,
Yes, and
oh, is
that
it?
must be how you got the build molecule.
Right, yeah.
Oh,
Yeah, I
that
got
is,
it.
okay.
So yeah. So we have been coordinating. In fact, Danny's considering longer term, but not this semester.
Okay, I was just.
But in the future, it's a great idea.
It wasn't clear to me that this was.
Right.
It seemed like it was in a vacuum, and I didn't know that.
So, what I was originally most satisfied with the original tutorial was this focus on the negative kinetic energy in the classically forbidden region. And I'm kind of similarly bothered by this, trying to build up analogies between classical particle-like behavior and quantum wave behavior, right? Because this whole business of transmission, reflection, and so forth, this is wave-like behavior that's being demonstrated. And, I'm thinking for example, if there were a sim that shows a water wave and the depth, of the water, gets less, then the wave slows down and so forth. So there's analogous classical wave behavior, and I believe I think you're trying to scaffold off, their intuitive understanding of particles, except that the particles doing something totally non-intuitive in that region. And so I'm thinking maybe the analogy would be better to make wave, quantum wave versus classical wave behavior instead of quantum wave versus classical particle behavior. You know what I'm saying?
Yeah. I didn't think to do that in the first tutorial, but yeah.
Don't water waves speed up and shallower?
No, that's why the crest is higher as it comes ashore, because it bunches up as the wave speed goes
Right.
up.
Wave speed, water speeds up when it goes through constriction
Channel.
pipe.
Right.
The thing was that we didn't want to spend too much time on the classical case in the first place, and I don't know how. The classical particle is pretty intuitive, and they get through that section, in maybe 5 minutes.
Right, but then you're saying in the quantum case, you don't want to believe the electron spends more time in the classically forbidden region than the rest of the wire.
Right.
It's a bigger amplitude.
I'm wondering if you need an explicit analogy like that at all. Water waves, again, is probably just as how water waves behave at a barrier is probably just as confusing as how quantum wave particles.
At what point do we have to start building up this intuition about what waves do?
Right.
We can't just base
What
everything on.
I'm saying is that there's already lots of intuitions that students have about what is going on in the simulation.
Right.
So the simulation is an analogy.
So you're saying skip the classical and just use the
skip
sim.
the classical. One of the things about games is that often they're self-contained. They have self-contained rule sets that you have to learn in order to play the game. And in a lot of games, learning the rules of the game is the game. And so, learning the rules of the quantum simulation and how that system works is part of the game. I don't think you have to have explicit classical analogies in order for people to understand things like bouncing, or reflecting, or
The
slowing.
whole purpose of the analogy was to motivate why the amplitude is greater.
Amplitude and wavelength in that forbidden region, having them, helping
not
them make
just the
sense.
amplitude, the wavelength, but the amplitude of the wave.
Why is it greater?
Well, we can talk about mathematically.
Right. So it has nothing to do with the classical.
Well, but
what I'm asking is, how does that help?
That's
help
interesting.
you?
No, that's what I'm saying. I think that's the only
It tells you
reason
it's
it tells
It's two things that both happen to be slower at the top in certain regions, but the why for that's completely different. So I'm not sure how that helps you.
Correspondence principle. Slow's got to be involved.
Yeah, I actually, I mean, so I really appreciate this, Charlie, but I sort of disagree with you. You want to develop intuitions around waves, but, we taught it, I like to think fairly effectively with class, to talk about kinetic energy.
Then I would want to see like a wave packet. What do they do with a wave packet? Not this plane wave business. Because
Well,
the
maybe
wave
this is a
packet's more
research
particle-like,
Right.
and you're going to talk about, if you're going to make analogies to particle-like behavior. then
It's
have
true,
to-
the correspondence principle is much easier to see in tunneling when you use a wave packet simulation.
Right. It's an interesting idea. So the other thing I would say here, so fix that, Danny, and then resolve that debate, which is it's a good one, and it's a really, the other thing is that, right, we might be misleading students in terms of their interpretations or intuition about interpretations, which is really what, part of what Charlie's getting at. But the other thing is, I would be cautious about using the sim as a tool to verify. I think it can be used that way, but it could also then just be like, well, oh, that's the back of the chapter where I look up and find that I've got the right answer or not the right answer.
Yes.
As opposed to I don't think this is a heuristic, but maybe, which is, can you use this tool as a key instrument to get to some end that I already have? Right, so I want to use this as a tool, not as an end, but as a tool for me to achieve some goal that I already have in terms of inquiry. And then it becomes an instrumental mechanism for me to investigate and play around with the space, and I learn the parameters of the tool, but the goals aren't to learn about the tool itself, the PhET simulation, but rather to achieve the ends that I have as a student, which is what these sort of challenges kind of play to. So if there's a way to sort of lever that versus to say that it's the object itself.
So this may be related. Every time Danny has worked on a homework assignment for a sim in my class, he and I, sit down in front of the PhET sim and spend an hour, 2 hours playing.
Right.
And we walk away feeling like we had a formula before. And now we have something else besides just it's like there's a new understanding of what that formula looks like or means or tells us. We've simply never had any idea of how to get students to do exactly what it is that we did.
Well, have you interviewed students or watched what they do if you say sit down and play with the simulation and tell me what you see that's interesting?
Or write an assignment for this class.
So you had an element of an assignment which was, the last part was tell us something interesting or, that, like, play for a while. You explicitly had that in an assignment, and as I recall, they almost all blew it off.
They blew it off unless it was extra credit, and then they asked serious questions.
I would suggest you could try lying to them and say, this is a new sim that has not been fully developed yet, and we want you to test it and see what you can find, and are there bugs and things like that.
Yeah.
So if you lie to them, they will explore it as though, do you know what I mean? Because that's what we do in interviews, and that's what we
It
see.
doesn't have to be a lie. You might change it if there are bugs.
Well, and another thing to play on, I really like that, Ariel.
Yeah, me too.
Which is, we need your help. It's always a very compelling way to start with students. It honors where they're at and what they have to add. But the other thing is I wanted to play on your ideas, Danny, which is why don't you work through the mathematics of it, solve this.
Yeah.
Now, we need you to play with the sim. All right, did we get the representation on the sim correct?
Right.
With our mathematics? How does this representation differ from
That's
the
what I meant
mathematics?
by
What is it that
line.
you see? And maybe even have them go meta on it a little bit, which is to say, what is it that this representation provides for you that the math doesn't? And
Or a real life demonstration.
or a real life demonstration
So they
of a
don't
plane
look at
wave
it as
contingent
just
on a
some
barrier
animation.
wall. Yeah,
They look at it as something they have to explore and see if it's right.
right.
Because when you see in interviews, they look at these. They look at these as if they don't understand something at first, they're questioning. Well, is it that I'm not understanding, or is there something wrong in the sim?
Right.
What's going on here? They really try to explore.
Take it
Ian?
apart.
Yeah. So you guys are moving really fast. So I'm thinking of the way elementary students learn math. A good paper is like the the idea of where students learn going grocery shopping, right? They go with their families. You can think of actually shopping for groceries if you were to go on your own as a simulation, right?
Yeah.
You try and buy some, you try and work out what's cheaper in your head. I mean, that's all on you. But they have this side where they're talking about it with their families. They're getting examples. To what extent are the students working with other people to make sense of it outside of the simulation? And how much might that play a part in that? Because that, I think, would be more important for them making sense of it outside of it than just them plugging in and getting some feedback, plugging in and getting some feedback over and over. They can get to it eventually, but like this model right here, we're all working together. It's not just you plugging in and getting some feedback from students and pulling back. I'm wondering if you're looking at their interactions with one another and how much that might actually influence.
Yeah, no, I mean, right now I'm just trying to get it to the point where they will have a good conversation. You know, like I don't know, I'm not trying to. Are you saying like how to guide what they talk about? And
No, just seeing what they talk about and how that might influence. And I mean, a good conversation from our perspective might be very different than a good conversation from their perspective. I mean, we have this high-level view of what science is and what we think they should be talking about, whereas what we think they're talking about may be super simple and we think it should be intuitive for them, and it may not actually be intuitive. It may be something that they need to get past as a roadblock before they can get to where we want them to be. So I think
you have at least two great points there. Is really really important. So one is, and in some sense, that's you said better than what I did, which is that would be the role of saying, hey, this is another representation that we can coordinate around beyond the math. So they're coming into this and they know the math. That is what the community is talking about. That, in some sense, is the shopping in the physics world, which is kind of crazy, but that's what we do, is solve math equations. Because we're all jealous of what y'all do in mathematics. But now all of a sudden you can say, hey, how does that make sense in terms of this representation that's being run on the simulation? Can you come back to the mathematics? Does this make sense? Did we get the simulation right? Did you get the mathematics right to re-coordinate about what you already know in that sense, to draw on what the community norms are about representation? So I think that's great. And then the other side is to say this form of discussion and discourse, can you engage in a way that is meaning-making and or that draws on those various forms of normative behaviors that we appreciate? And for that, we can say, yes, we have looked at it. In some sense, that's what Danny has done. The discussions that have happened so far is that a sine wave? Yes, that's a sine wave. Is this that? Is that? Those are all mechanical and things that are not at the higher level that we want, which is as opposed to the students who in fact didn't use the sim that were trying to make sense of, all right, I know I've got to reconcile these. If you recall the mathematics, they say, I know I've got to reconcile with what my intuition says versus what I know is right. That's what we want the sim to be able to do. And I think going back and using those norms. So those are the two different pieces, getting people to talk in ways that are meaningful, but then also draw on the norms of what exists within these local cultures. In this case, it's math. Ironic. Yeah. Okay, so do that too.
Another crazy idea would be have one student be the interviewer of the other student learning the sim. Like, hey, one student has to be quiet and just kind of watch and observe what the one person is doing, and have them talk aloud about the sim, and then have them switch roles or something like that.
I do that in some mathematics. So we had a teacher handed a student notebook that detailed something along the lines where they had partnered the students up and had one be a speaker and the other one be a recorder. And so the speaker was their job to kind of like explain their thought processes and how they're doing this. The recorder was to either like help them get further in doing that, and then write down kind of or skim out the important parts, and then they would switch. And so it looked from what she submitted to us, yeah.
Interesting.
And talking about something, have you read any of Jim G's stuff? Focus on that as much as you got.
All right. Well, thanks very much, Danny. Good job.